In this solved example, we will show how to use the effectiveness NTU method aided by the graph to solve and analyze the heat exchanger. The problem is as follows. Hot exhaust gas enters a fin tube crossflow heat exchanger at temperature of 300 degrees Celsius. So this is then I say T hot in and leave at 100 degrees Celsius. So this is T hot out. It is used to heat water at a flow rate of 1 kilogram per second from 35 degrees Celsius. So this must be T cooled in, and it exits the heat exchanger at 125 degrees Celsius. So this must be 3 cooled out. Assume Cp of water is 4.2 kilojoule per kilogram Kelvin and Cp of gas is 1 kilojoule per kilogram Kelvin. You can also assume here, given the approximate transfer coefficient 100 watt per square meter per Kelvin, the question is determine the required heat transfer area. Before I solve this problem, I want to tell about in some problem, okay, we given the Cp value and also the U value, okay, the Cp value, and this is actually the U value, okay. But in the reality, we don't know. So in this case, you need to use appropriate physical property table of liquids to find out. And you will find what is the typical Cp of water at given range of temperature, the Cp of gases at given range of temperature, and what is the range of U for that kind of configuration. So what for that kind of process, the heating of the water, for example, the heating of the oil and so on. So you need to be able to find out the real value, to estimate the value if they are not given. In reality we don't know. So in reality you need to find out yourself. Probably in the exam I will also not give this value. As such, you know that in the reality you will not get the value as easy as in this problem. Okay, so note on that. To be able to solve this problem, a graph, my favorite method, we use graph. But first of all, we need to illustrate the flow configuration. We know it's a hot exhaust gas, so this is hot gases. Is the hot. It's entered at 300 degrees Celsius. It exited 100 degrees Celsius. We know the Cp of gases is given here 1 kilojoule per kilogram Kelvin. If it's not given, you need to find out. You can assume, okay, gas and liquid. You can assume, okay, the appropriate value. The mass of hot we don't know. So on the other side, the cold stream is actually water. So I'll say this is water. It enters T cooled in at 35 degrees Celsius and T cooled out at 125 degrees Celsius. We are given the mass flow rate of the water, 1 kilogram per second, and we also given Cp of water of 4.2 kilojoule per kilogram Kelvin. So in the effectiveness NTU method, we use the same step as before. First of all, we need to find out the Tmax. Tmax must be this guy minus this guy, that's Tmax, equal to 265 degrees Celsius. Then we calculate one by one heat flow capacity of the cold and heat flow capacity of the hot stream. We can easily calculate for the cold side, because all of the information is given, Cc equal to MC, sorry, this is supposed to be MC, times Cpc. Then we end up with Cc equal to 4.2 kilowatt per Kelvin. The next one, we cannot directly calculate Ch. We need to first find out what will be the Mh here. So we use the energy balance on the hot and liquid side to find out what will be the Mh, and here first then we go to find out the Q actual, Qc times delta Tc. We find out that actually the heat that is transferred from the hot stream to the cold stream is 378 kilowatt. Then we can use this value to find out what is the required mass flow rate of the gas. It's enough with 1.89 kilogram per second. Now, since we know mH, we'll be able to calculate the CH, which equal to mH times CPH, and we find out it is 1.89 kilowatt per Kelvin. So after calculating CC and CH, we need to identify which one is Cmin and which one is Cmax. Any one that is bigger is Cmax, very easy. So this one then is a Cmax, C then becomes Cmax, while CH then becomes Cmin. So next we calculate the C relative, which is equal to C min divided by C max. We find out the value is 0.45. And lastly, before we go to the graph, we need to find out the effectiveness value, which is equal to Q actual divided by Q max. And all of the value required to solve this equation is available. We end up with 0.75. So finally, we need to choose the appropriate graph that fit to the problem. This is a fin tube crossflow heat exchanger. So I have here a fin tube crossflow heat exchanger. So we know the C value, C relative value 0.45. So it's something between this guy and this line. Okay, this line and this line. And then we know the E is 0.75. So somewhere here. So I just draw the line of that. Okay, and this is the point where actually the C and the epsilon cross, and we pull it down to find out NTU, and the NTU here is about, I think it's a 2.1. If you say 2.05, I'm okay with that one. So then we key in to the NTU equation equal to AU C min, and then we rearrange the equation, and finally we can find out the ultimate solution for this problem, which is to find out the overall heat transfer area. A equals 39.69 square meter.